So good morning, everyone. It's a pleasure and an honor to be giving the talk at QIP, and I thank the steering committee of QIP for inviting me to give the talk. I have to say that I'm quite sad that I'm not able to give the talk in person and meet everyone. But this being said, I'm also very happy that many more people have the opportunity to listen to the talk. So I'm going to tell you about a result in complexity theory. That's the equality MIP star equals RE, and applications of this result in particular to a problem in the foundations of quantum non-locality that's known as Tsirelson's problem. And the work that I'll present is joint work with 4 co-authors. There's Zhengfeng Ji, who's at UTS, Anand Natarajan, who's at MIT, John Wright at UT Austin, and Henry Yuen at Columbia. And I'm not sure any of them is around right now due to time zone conflicts, but you can find them in the Slack later or in the corridors of the online space. So feel free to ping them just as me if you want to discuss anything related to this talk. So because it's quite early, I imagine a lot of you might still be scrambling through coffee or other morning duties. So let me start slowly with some memories. So as I was preparing the talk, I was brought back to my first QIP, actually the first QIP in which I gave a talk. This was QIP 2008 in Delhi. I was a first-year PhD student, and I was presenting work that I had completed during my master's. So I managed to dig up the slides from that presentation, and this is the first slide. It's a little bit boring. This was joint work with Kempe, Kobayashi, Matsumoto, and Toner. So I don't know if any of you were in Delhi in 2008. Actually, probably some of you were, but not all of you, because I don't think there were 3,500 participants at QIP 2008. Even if you were there, I doubt that you remember my talk. But if you did remember my talk, and this is the title slide, then it would be easy for me to explain what happened in the intervening 13 years. Because the title for the present talk could be written this way: entangled games are harder to approximate. So this is what we gained in 13 years. And maybe that's my message to the students in the audience that, if you don't manage to solve the first problem that your PhD advisor gives you when you start your PhD, if you don't manage to solve it right away, then this is okay. Don't worry about it. There'll still be QIPs 13 years from now. And who knows, by then, maybe they'll be in person, so it'll be even better. Good problems are forever. All right, so of course, in the 13 years, a lot of things happened, and this is just a sample of QIP talks and results on which my talk is building. So you don't really need to pay attention to this right now. I'll get back to most of these results throughout the talk. This was just a chance to give you some pretty pictures from previous QIPs, because there might not be any more pretty pictures in the talk, so just watch them. And now let's get started. Actually, even before getting started in earnest, I want to spend a few minutes just trying to give you a sense for what the title result is, this equality, MIP star equals RE, because I know this is like just letter soup for most people. So in complexity theory, we strive to classify computational problems according to different measures of difficulty. The most well-known complexity class is the class P of problems that can be solved in polynomial time. If you allow randomized polynomial time, you get the class BPP, and quantum polynomial time, that gives you BQP. So example of problems in this class are simple graph problems, such as testing connectivity, some number theoretic problems, such as primality testing or factoring, if you allow a quantum computer. Now, not every problem is solvable, and complexity theorists try to identify features of problems that might be hard, but still make these problems interesting, something special about them. And a particular feature that has proven productive to study is the notion for a problem to have efficiently verifiable proofs. So for example, if you take the problem of coloring a graph, this might not be easy because you'd have to, a priori, you'd have to try all possible colorings. But if someone gives you a coloring of the vertices of a graph, it's easy for you to go through all edges and to check that the endpoints of any edge are colored differently. So graph coloring is an example of a problem that lies in the class NP. Again, if you allow randomized verification, it's called MA. Quantum verification is called QMA. These distinctions are not too important right now. So this idea that there are problems that might not be efficiently solvable, but still admit efficiently verifiable proofs, there's of course a foundational observation or question in complexity theory, it's the P different from NP question. And it's also a question that plays a role in this talk. However, the complexity classes that we're concerned about are much, much bigger than these two. That's why I drew them so small at the bottom. So let me talk about them. First of all, you have the class RE. RE stands from recursively enumerable. At a high level, this is just a collection of all problems such that true answers can be recognized in any amount of time whatsoever. So this is a huge class. It contains any kind of problem such that whenever the answer is yes, you can eventually figure it out. But there's no question of time. So there's no difference here between randomized computation or quantum computation. The class of BRE, QRE, they're the same because there's no restriction on time. So the class contains many, many problems. So for example, graph non-coloring. A fun problem isn't there is just deciding whether a candidate theorem is provable in some set of axioms, such as Zermelo-Frankel set theory. The class is so big that it even contains undecidable problems. So the halting problem is complete for the class. And this is just the problem of, given a piece of code, does the code ever end or not? So if the code ends, you can figure it out because you just run it and it'll end, and then you'll know that it ends. This is why it's in the class. It fits the definition. On the other hand, if the code doesn't end, then there's not going to be means for you to verify this. And this is why the problem is undecidable, as was shown by Turing in the 1930s. This is a huge class. And the other class that we're concerned about, MIP star, is a little bit harder to define, so I'll define it formally only later. But at a high level, what you can remember from it is that it involves a notion of efficient verification. But this notion of verification is a little bit special because it involves interacting with quantum provers sharing entanglement. So now our result is that these two classes are equal. And from a complexity theoretic standpoint, that's a very interesting result because it states the equality of two collections of problems that are defined in very different ways. So RE is this very big class that basically contains any problem that you could think of, unless you try really hard to find a problem outside, it'll just be in there. And there's no notion of efficiency in the definition of the class. MIP star feels much more contrived. In particular, there's this notion of efficiency. Polynomial time comes in. MIP star are problems that should be verifiable in polynomial time in some model of interaction. And so what's surprising is how would polynomial time come into the picture, right? And so the equality makes it come in some way, and that's what makes it interesting. And I'll try to give you some understanding of that as the talk progresses. Now, if you're not a complexity theorist, and most people are not complexity theorists, let me give you a few other reasons to care about the result. So some consequences of it. One consequence that I'll touch upon in much more detail is a negative answer to Tsirelson's problem that asks about the difference between two ways of modeling non-local correlations in quantum mechanics. Another consequence is to a famous conjecture in the theory of von Neumann algebras called Connes Embedding Problem. So there's a refutation of that conjecture. Other consequences that will become clearer as I unpack the result for you are very efficient tests for high-dimensional entanglement and complicated quantum computation. And finally, there's a fourth consequence to Navascues, so noisy intermediate scale quantum systems. So we give a provable advantage for, yeah, okay, I'm joking. No practical applications in this talk, sorry about that. Luckily, there'll be a lot about this in the remainder of the conference, so I invite you to attend the other talks to learn about practical applications. This talk is mostly a theoretical talk. Okay, so let's get started. That's the plan. First of all, I want to tell you about Tsirelson's problem and quantum correlations. Then I'll introduce our approach to Tsirelson's problem that goes through complexity theory. And then the main chunk of the talk will be explaining the complexity theory that goes into the proof of the result, and that's the notion of quantum multi-prover injective proofs. And I hope that I managed to save enough time at the end to discuss a lot of open questions. All right, so let me first tell you about about Tsirelson's problem. So we're all familiar with the notion of non-localities. This is the idea that you can initialize two systems, quantum systems, in a certain way that if you make local measurements on these systems, then the outcomes of the measurements are correlated in a particularly strong way. So this idea was made precise in the work of Bell in the 1960s. And here's the kind of experiment that Bell considered. So you imagine that you have two quantum particles, or could be more particles, but they're separated into two chunks. And then as an experimentalist, you get to make a certain number of local measurements on each of the particles. So measurements on the first one are indexed by some variable x, measurements on the second one by some variable y. And when you make these measurements, you collect outcomes, A for the first one, B for the first one. If you imagine repeating this experiment many times, you can collect statistics and estimate this family of distributions. For any pair of settings, x and y, there'll be a distribution on outcomes A and B, and this is what I denote P of AB given measurement settings, x and y. So that's what I'll call a quantum correlation throughout the talk. Bell's theorem is that there exists such families of distributions that have a quantum model, but don't have a classical local hidden variable model. Right? So this is what we call quantum non-locality, this kind of distributions. Now, 15, 20 years later, Tsirelson in the 80s was interested in understanding what are the limits of what's achievable specifically quantumly. So Bell's theorem separates classical from quantum, and Tsirelson wanted to understand how far can we go in the quantum regime. And he was a mathematician, so he had to model how these quantum correlations look like. And Tsirelson came up with two natural ways to model quantum correlations. The first way I'll refer to as the tensor product model. So this is kind of like textbook quantum mechanics. You associate a Hilbert space to each of the quantum systems. Then there's a quantum state that lies in the tensor product of these Hilbert spaces. Each measurement on each particle is modeled by a projective, or not necessarily projector, sorry, positive operator valued measure, P or Q on the relevant Hilbert space. And then the probability of getting outcomes A and B is just given by the Born rule as written on the slide. But he also observed, and you can think that this is inspired by quantum field theory maybe, that there's possibly a more general formulation which consists in saying that, forget about two Hilbert spaces in tensor products. Let's just have one Hilbert space for the universe. Both particles are in the same Hilbert space, so there's just a state in that Hilbert space and measurements acting on the Hilbert space associated with each particle. But then this notion of locality is realized mathematically by requiring that measurements on a distinct spatially isolated particles should commute. And so that's what I wrote at the bottom there is a commutator. It says that P and Q commute. At first, Tsirelson thought that these two characterizations, in fact, are the same. The reason is that you can prove, it's a small exercise in algebra to show that in case the Hilbert space is required to be finite dimensional, then these two, there's no more generality in the second way of writing things, which I'll refer to as the commuting model. But if the Hilbert spaces are infinite dimensional, then the equality is not less clear. And when Tsirelson was pressed to explain whether these two things are equal, he wasn't able to do it. And so he posed it as a problem. And so this, I'm just writing it in Tsirelson's word, but this is what's referred to as Tsirelson's problem. Are these two different models for quantum correlations the same, or are they not? So we can look at it a little bit geometrically by introducing sets of correlations. So the set that I drew in blue, that I'll call it the tensor set. So each point in the square or in the set is just a vector of probabilities. Okay, so each of these correlations I can represent is just a bunch of probabilities, the probability of each possible outcome for each possible setting, and such a vector of probabilities I represent as a point. And then among the points in my square, some of them are realizable in the tensor product model. That's the ones in the blue set, and some of them are not. Okay, and so we can similarly draw another set for the points that are realizable in the commuting model. So what's known about these sets is that both of them are convex, as drawn on the figure. That's not too hard to see by taking direct sums. It's also not hard to see that the tensor set is included in the commuting set. What's harder is that, well, showing that the commuting set is closed, that's again exercise. What's a little bit harder, or much harder, is to show that the tensor set is not closed. This one's shown by Slofstra 2 or maybe 3 QIPs ago, using pretty involved techniques coming from group theory and embedding groups into correlations. So if you don't know what closure of a set means, it's not too important. The point of this is that because one set is closed and the other is not, they can't be equal. So that's the first answer to Tsirelson's problem. These correlation sets are not the same because one is closed and the other is not. But then you could say, okay, but what if the difference is tiny, right? The difference between a set and its closure is not something that you can notice. It's just a question of limits. So here's what's referred to as the strong Tsirelson's problem. We just make both sets equally nice, take the closure of the first one and ask whether for any number of measurement settings, any number of outcomes, n and k, do the two models coincide, or does one allow you more flexibility than the other? Some reasons that this question might be the right question to ask come with through a series of equivalences that were proven starting in the 90s, but more around 2011 through the work of Fritz, Yuen et al. And Ozawa. They show that the strong Tsirelson's problem, as I formulated it, is equivalent to a huge family of conjectures in mathematics in operator algebras. The most famous one is called Connes Embedding Problem from the 1970s. And I'm not going to explain what this is. You can think of it as a finite approximation problem. It's asking if certain kinds of infinite dimensional von Neumann algebras might have finite dimensional approximations by matrix algebras. And to say the truth, this problem was kind of not so important for a couple of decades until Kerperg gave an equivalent formulation in the theory of C-star algebras. Again, I'm not explaining this. I'm only putting it on the slide so that you see the tensor product. And so when you see this, you think, okay, well, now we're getting close to Tsirelson's problem. And indeed, all these conjectures and many more in group theory, in the study of free entropy are equivalent. So if you answer any of these conjectures, then you answer the other. And this is what we're going to do. We're going to answer Tsirelson's problem in the negative. And so all these conjectures here have negative answers. Okay, so let me get to the heart of it. Earl, you're still there. You'll interrupt me if there's a question or something is wrong.
Yeah, I'm still here. No.
Okay, cool.
No.
Cool. Yeah, you never know.
There is one question actually that's just popped up. Is
Okay.
CO times an open set?
I'm not sure that's known. You should ask William Slostra about this. My guess is not. Definitely not for small values of n and k. My guess is not, but I'm not positive. Yeah, thanks for the question. Okay, so our goal is to give an answer to Tsirelson's problem, and you maybe notice that so far there's no notion of computation, definitely no complexity theory, no complexity classes, nothing. So how are these going to enter the picture? The very high level idea is that if you want to understand an object, it helps to ask the question, how do I compute this object? Not only because, if you can compute, then you can do experiments, small experiments, gain some intuition from small examples. That's one reason. But another reason is that very often coming up with an algorithm, an answer to this question, how do I compute, gives you some different insights into the problem that you want to study. So what is there to compute here? We have a set. I mentioned it's a convex set. So the natural thing to do about it is to take a linear function like this lambda here and ask about the problem of optimizing this linear function over the set. So that's a very well-known problem. This linear function is just a Bell inequality, and the maximum over the tensor set, this is a value that I'll call omega star of lambda. That's just the maximum violation of the inequality that's allowed in quantum mechanics and specifically in this tensor product model. Okay. So it's a quantity that many of you will have seen, but I can just define it geometrically like this. Okay, take a line and take the maximum value that this linear function has over the set. Okay, so now we have a quantity that we can ask how to compute that quantity. And so let me tell you about what's known about this. How do you compute the maximum quantum violation of a Bell inequality? Or I'll just say the quantum bound for short as the talk progresses. So first thing that you can do is kind of try exhaustive search. So you'll just fix small dimensions for your Hilbert space, maybe bigger and bigger. Then you'll discretize the Hilbert space in a certain way, maybe get finer and finer discretizations, and then search over all possible states and measurements in your discretization. And as you allow the dimension to grow and make the discretization finer, then you'll get better and better bounds. And so this gives you a sequence of lower bounds that grows, and you can show that that sequence converges to the quantum bound. It's not completely trivial because my definition of the quantum bound doesn't require the Hilbert spaces to be finite dimensional. They can be infinite dimensional. So it's a valid question to ask whether considering only finite dimensional approximations, you will converge to the right value, but you do. Again, it's an exercise. You can show that this is the case. However, that doesn't give you quite an algorithm because you can compute these lower bounds, get your dimension bigger, discretization finer, but you never have a sense of how well you're doing. You're doing better, but how far are you? So in order to be able to estimate that, you need a matching sequence of upper bounds, and then you'll just look at how far you are, and this will give you an estimate. So the best known way to obtain upper bounds on the quantum value is referred to as the NPA hierarchy. NPA stands for Navascues, Pironio, and Assin. I'm not going to explain that because it's not so important for the talk. You can just think of it as a sequence of optimization problems of whose size grows and grows and grows. Each of them can be solved in time proportional to its size, and the bigger it is, the better the upper bound it gives you. Okay, so now what's interesting is that what's known about this sequence of upper bounds given by the NPA hierarchy is that it does converge because it's a decreasing sequence of upper bounds, but not towards the quantum bound. Instead, it converges towards the commuting bound, which is the largest quantum violation of your inequality that's achievable in this commuting model, not necessarily tensor products. So now the question is, do these two things match or not? Is there a gap for any Bell inequality between these two algorithms? So there's two possibilities. It could be that for every Bell inequality, exhaustive search and the NPA hierarchy eventually converge to the same answer. Then it would mean that for every Bell inequality, the tensor bound and the commuting bound are equal. And so the blue set and the purple set would have to be equal. And that would give a positive answer to Tsirelson's problem. Or it could be that these two, sorry, I wanted to mention that's definitely what seems to happen in practice. So these algorithms are used a lot in practice. And if you try test examples, it seems that you have to spend a lot of computational effort, but eventually you get two lower bounds and upper bounds that match. Okay, but that's just small examples. So it could also be that these two procedures, at least for some Bell inequality, do not converge to the same value. And that would be a proof that Tsirelson's problem has a negative answer. Okay, so that gives you an idea of how you might try to prove or disprove Tsirelson's problem, show that these algorithms match all the time or sometimes do not. Unfortunately, doesn't seem to be quite a viable approach because it's very hard to analyze the algorithms, say anything special. And so the approach that we're going to take in the talk in our work is to prove something stronger. And this is something that was suggested in work in a slightly different context by Fritz, Netzer, and Tom, which is to show that in fact, no algorithm would be able to compute the quantum bound. So it's not only that exhaustive search and NPA hierarchy don't get you there because there's sometimes a gap, but it's also that there's no way to improve the NPA hierarchy so that it always converges to the quantum bound. If there was, then the quantum bound would be computable because you'd have an algorithm. But what we're going to show is the stronger fact that there's no algorithm, that this value is uncomputable. So you could ask, okay, well, why do we set ourselves on proving something harder? The reason is that it's a cleaner problem and that it turns out that complexity theory for completely independent reasons gives us an avenue to proving the problem, to showing that the quantum bound is uncomputable. And so that's what I want to explain next in the third part of the talk. So maybe just to go back there, where we're going is that I want to show that this quantum bound is uncomputable. By the previous observations, this will give a negative answer to Tsirelson's problem. The reason I'm going to show that it's uncomputable is by going to complexity theory and studying this notion of quantum interactive proofs. And then a little bit later, I'll pull it back and explain to you why that's the right notion to study this question. So we're making a little bit of an aside now. I need to tell you something about interactive proofs.
So Thomas, since we're at a segue point, there is a question in the Slack relevant at this point, which is what is known about the rate of convergence for the quantum value associated to the CO times with the increase of local dimension used?
Yeah, nothing. So if there was something known about the rate of convergence, then this would give you an algorithm. It would show that the value is computable because for any small accuracy epsilon, you'd know exactly how many steps you need to run, like how far you need to go in the dimensions or the discretization to be within epsilon. And so that would fit the definition of this value being computable. So nothing is known about this rate, and this is why there's a chance that the value would not be computable, because you can go as far as you want. Maybe I should have clarified that about the important parameters. So these correlations that I'm talking about, they involve a number of settings and a number of outcomes, and k. These are not necessarily large. Everything that I say applies to n and k equals to 5. Okay, so the difficulty is not that I'm blowing up the number of settings or outcomes. The difficulty is really what the question is pointing out, which is that even for only 5 settings, 5 outcomes, I have no sense at all of how large a Hilbert space I might need to come even close to the largest quantum violation. So thanks for the question. I'll go on?
Yes, please.
Okay, so I'm going back now right to the start of the talk. I introduced these classes BPP, BQP, and also MA and QMA. I just want to go over them again, give you a slightly different pictorial representation. So BPP does just all problems that have efficient algorithms that can represent in this way. There's an algorithm, the algorithm gets an input, it runs in randomized or quantum polynomial time, and then it has to produce an answer. And these are some examples. Now the class NP or MA and QMA, I can represent in almost the same way, except that I'll call the algorithm a verifier. V is for verifier for the following reason. I think of my verifier as given an instance of the problem that it needs to decide, but now it's not going to have to do this by itself. It also receives a little bit of possible help from a prover. The prover is some unbounded entity that provides the proof. Could be a classical proof or a quantum proof, depending on the model. And now the verifier, still in randomized or quantum polynomial time, has to decide whether this proof is a valid proof for the statement that it's trying to decide. Again, here are some examples of problems that fall in this class. I want to point out that the definition has a slight asymmetry that's not present in BPP. So here the requirement is really the intuitive requirement that you expect of a proof. Okay, valid statements should have valid proofs, and invalid statements should not have any valid proof. Okay, what I just said is not symmetric. You're not treating valid and invalid statements in the same way. The only difference here in MA and QMA that it's not only that we want there to be valid proofs, we want these valid proofs to be efficiently checkable. Okay, so these two classes and the importance of them, that's like 1970s complexity theory, and complexity theory was born in the 1970s. So a lot of things happened since then. And in particular, people worked hard to understand if this, what I is just on the slide, is the right characterization of efficient verification, or if you could not make it a little bit broader. For example, you can take the problem of graph non-coloring. Okay? How do you prove that a graph is not colorable? As far as we know, you can't do it in the MA or even QMA model, because you have to convince me that there's no coloring at all. How do you do that? And a major realization of the 1980s is that there are some problems such that graph non-coloring that don't seem to have static proofs, but they have something else that's called the interactive proof. So the only change that I made in my diagram is that the verifier now does not only receive information from the prover, but is also allowed to ask questions, clarifying questions. You know, could you say more about this? Could you say more about that? What if I ask you this? Things like that. The difference between IP and QIP is whether the verifier and the communication are classical, or the verifier and the communication are quantum. And quite surprisingly, some problems such as graph non-colorability and even the whole of p-space, so all problems that can be solved in any amount of time, but polynomial amount of space, such as Go. Go is some problem associated with the game of Go, have interactive proofs of this form. So it seems like we're capturing more problems like this, but in fact, in complexity theory, there's no strict separation between p-space and p, so we don't know for a fact that this class is bigger. However, if you make one last modification, then you do get strictly bigger verification power. And that's a little bit of a surprising modification. It's the modification of allowing the verifier to interact with two provers. So you could ask, what's the point of two provers? Like, how do you get more information from two guys than just one guy? You know, you can just like talk with the one guy a little bit longer. But you have to remember that the point here is not really to get information, from the provers. The only information we're trying to decide on is whether we say yes or no, whether the problem has a positive or negative answer. That's just one bit of information. The point of the prover is that you need to verify them. And having two provers is a little bit like having access to two prisoners in separate rooms. You can start playing little games with them, do some kind of consistency checks on the answers that they give you. And this gives you more verification power. How much more was demonstrated in a famous result by Babai, Fortnau, and Lund. They characterized the verification power of this class as all languages in non-deterministic exponential time. QMIP, again, is like MIP, but I make the verifier in the communication quantum, and you can show that there's no additional power to quantum in this setting. Now, this is a very surprising result. It's surprising because languages in NXP, in particular, this contains exp, they're languages that you cannot solve in polynomial time, for sure, okay? They need exponential time for sure to solve. Still, in polynomial time, by interacting with these provers, you can verify inputs to these languages, and you make mistakes with arbitrarily small probability. All right, so what does this have to do with our problem? Well, I went a little bit fast here when I introduced these two provers. I said, it's like prisoners, you put them in different rooms. Okay, if you're in the audience, if you're someone familiar with quantum mechanics, your question is, okay, well, how do you model exactly be in different rooms, okay? And so this brings us back to exactly Tsirelson's problem. Is there one Hilbert space, two Hilbert spaces? Do these provers share entanglement? These kinds of questions. So the fact that you could refine the model or tweak it in this way by possibly allowing entanglement between the provers, this is an observation that was first made, I think, in a QIP talk by Cleve, Oye, Toner, and Watrous in 2004. And they introduced the class that we're concerned in the talk, MIP star. So that's the class of all languages that can be efficiently in classical or quantum, if you talk about QMIP star, polynomial time, be verified by interacting with two provers that do not communicate, but are allowed to share entanglement. So the fact that I allowed entanglement now to the provers, it's not at first clear what difference it makes. One way to think about it is just that they have a broader set of strategies available to them than if I didn't give them entanglement. And so this broader set of strategies is going to influence the verification power of the systems that I might have before. Okay, so I want to explain in just 3 lines, just clarify the connection between this system of interactive proofs and our problem. So it's easy to see. So take a verifier for an interactive proof system of this form and ask the question, what is fixed in problem instance Z? And ask the question, what's the maximum probability with which provers can convince this verifier to say yes? Okay. And so if you're talking about a valid verifier, if this maximum probability is large, it means that the answer should be yes. There is a way for the provers to be accepted. If the answer is, the probability is small, then it means that the answer should be no. There is no way for the provers to be accepted. Well, if you just write this, so it's just a supremum of all possible strategies. Let's imagine for simplicity that there's a single round of interaction. In fact, I'm making this simplification throughout the talk. So this is just the distribution with which the verifier chooses its questions. And then I sum over all possible valid answers of the probability that the provers give me these answers. Okay, that's just writing out the maximum probability that the verifier accepts in this interactive proof. Now, the probability that the provers give me a particular pair of answers to a particular pair of questions, that depends on my model. But if I take the tensor product model, then I can write it as we did earlier, an expression of this form. And now I'm taking the supremum over all Hilbert spaces, over all states, over all measurements on these Hilbert spaces. And of course, now you recognize the expression that appeared earlier in the talk. All these coefficients, the distributions and the indicator of an answer being correct, I can sort of like squash all this into just a single real number. And that allows me to define a linear function, and I could call it a Bell functional, or the coefficients for a Bell inequality. And so you've seen that to any interactive proof, I can associate a Bell functional that has a special form. In particular, the coefficients are non-negative, such that the maximum acceptance probability in the interactive proof is equal to the largest quantum violation of the Bell function, of the Bell inequality. Okay, so Cleve and et al. Observed this. And so this gives you an avenue towards trying to show that this quantum value is difficult, because now you've equated, or actually reduced, the problem of deciding these quantum multiproof interactive proofs to the problem of computing the quantum bound. So if you manage to show that the class MIP star contains harder and harder problems, by the correspondence that I explained, you'll have shown that this quantum value is harder and harder to compute. In particular, if you manage to show that MIP star as a complexity class contains undecidable languages, you'll have shown that the quantum bound is uncomputable, which is our goal. Okay, so new goal, try to show that MIP star is a very big class, contains very hard languages, including undecidable languages. So what's known about this? So with Ito in 2012, actually, I think this was QIP 2013 in Beijing, we did a first step. First step was to show that the class with entanglement is not smaller than the class with entanglement. So we showed that MIP star contains the classical MIP, which, as I told you before, is equal to NX. So that's already pretty hard, non-deterministic exponential time, but it's not uncomputable yet. So then there's a lot of works that in the interest of time, I'm skipping. There's references. I'll get to references at the end of the talk. But just 2 QIPs ago, Natarajan and Wright did another major step. So they showed that MIP star contains problems in non-deterministic doubly exponential time. So that's like exponentially bigger than it was before. And in particular, it's exponentially bigger than the classical class. So I'm going to tell you a little bit about their result on the next slide, because it's crucial to understand what we did, which is kind of bootstrap it. So repeat, iterate their result, and then take some kind of a limit that I'll try to explain later, in order to obtain the containment that's the focus of the talk of RE and MIP star. And as I mentioned in one of my first slides, RE contains the halting problem. The halting problem was shown undecidable by Turing. And so once we've shown the inclusion of RE and MIP star, then we're done. We've refuted Tsirelson's problem.
Hi, Thomas. Sorry, there's a couple of questions on the theme of how can 2 provers be more powerful than 1 prover? So maybe you can just say something to that.
The question is not, it's kind of hard and you know, without getting into the details of the proof system, I think the intuition is really, again, it's not, when you say how can 2 provers be more powerful, these provers are infinitely powerful. So they're not more powerful in terms of their knowledge. But that's not important. In all cases, the prover knows the answer to the problem you're trying to solve, okay? The problem is that the prover might try to convince you to make the wrong decision. Could be that the answer is no, and still they're trying to cook up some fake proof that you'll accept. Okay, so the goal in the verifier is to make sure that they're not being cheated by the provers. And this is why, for that reason, 2 provers are more helpful, because you're going to start asking, you know, adaptive questions to one prover, and this prover is maybe answering adaptively too. And at some point you could say, you know, stop, what if I ask a related question to the other guy, and kind of like check you against each other. And because you're not talking, the other guy doesn't quite know what I've been asking you. And so I'll you know, enforce some extra checks in this way. So very high level, this is what it buys you. Lower level, it's a lot of algebra. Okay, so let me go on. I have a couple of slides. So the first slide is trying to give you like some very rough idea of how Natarajan and Wright obtained their result, because it's a very nice idea. The idea is start with kind of a blown up version of an interactive proof system with 2 provers. Let's say it's just a classical interactive proof system. So I blew up everything to exponentials. So my verifier is exponential time. And because it's exponential time, it can verify languages in non-deterministic doubly exponential time. Okay, so that's our target, but we want to achieve the same verification power with a single verifier. So what we actually have access to is not this big exponential time machine. We have this small polynomial time machine. And the idea is going to be, well, the provers are infinitely powerful. So why don't we offload a little bit more work to them? We're going to ask the provers to run the large exponential time verifier for us. So I'm breaking it up, the computation that the exponential time verifier was supposed to make, into 2 provers. And the small verifier is going to interact with these 2 provers, trying to like guide them through doing exactly the right thing. So what's the right thing? Well, first of all, I have to somehow find a way to make them generate the exponential size questions that the exponential time verifier would have generated. Then I have to let them locally compute answers to these questions as the original provers would have. And then I have to make them convince myself that the answers to these questions are correct. So as you can imagine, doing this is not a trivial thing at all. The idea of delegating complicated computation from the verifier to the provers is an idea that dates back to a paper by Wright, Unger, and Vazirani. But what's new in the Natarajan and Wright result is that they managed to do this extremely efficiently with a small verifier that's exponentially more efficient than the big verifier. There's two main ideas that go into the proof. The first idea is how do you make sure that these provers generate questions in exactly the right way? And this builds on the area of self-testing. So using entanglement in order to generate very specific kinds of correlations. And the second main idea is how are these provers going to report the answers, because the actual answers are exponentially long. And so what they have to do is prove that they are able to generate the correct answers without actually giving you the answers. And so this is ideas that tie into this theme of efficient verification, and you can solve that step using techniques from probabilistically checkable proofs. Okay, so I'm not going to say more about the result in the interest of time. Let me talk a little bit about what we add on to that. So if you understood what I said, there's kind of a natural idea, which is to say, you've just explained to me that you can take a big system and then kind of squash it. Can you repeat this? Can you start with something even bigger and then squash it twice, or something even bigger and squash it 3 times? That idea of recursively applying the steps is an idea that was presented, I think, last year, a paper by Fritz et al. And this is the first thing that we do. We find a way to iterate their construction, and in this way put bigger and bigger non-deterministic time complexity classes in MIP star. There's a difficulty that I'm completely glossing over, which is that when you do this, when you start iterating things, you really have to make sure that there's kind of a normal form for your verifiers that you're able to iterate over, that no parameter starts getting completely out of hand. The main challenge in doing so was to identify a class of distributions that you can test using entanglement, and moreover, you can test that class of distributions using questions that come from the same class of distributions so that you can iterate the procedure. I think that's an interesting contribution, technical contribution of what we did. And now once you've done that, you're not quite done because getting you arbitrarily large time complexity classes doesn't give you undecidable languages. So there's one last step that I have to gloss over, but the last step, you can think of it as a very high level as just taking a fixed point of the procedure that I was describing before. And through this fixed point taking, which is a little bit subtle, it involves taking the right representations of the verifiers and the right presentation of the compression procedure that I was describing. But by doing so, we're able to get at the final result, which is a procedure such that given as input any Turing machine, so think of this Turing machine as just a description of an algorithm. From the Turing machine, it computes the description of a verifier, or you can just think of it as the coefficients for a Bell inequality, such that if the Turing machine halts, then the largest quantum violation is 1, and if the Turing machine does not halt, then the largest quantum violation is at most a half. Okay, once you've done that, you've shown that the halting problem is in MIP star because the halting problem is complete for RE. You've shown that RE is included in MIP star. I didn't really say explicitly that MIP star is contained in RE, so you do get equality as announced on the title slide. The fact that MIP star is contained in RE just follows from the fact that this exhaustive enumeration algorithm from below converges. There's no bound on the amount of time, but it does converge. That says that MIP star is in RE. Okay, so let me briefly summarize, and then I'll, I think maybe I still have 2 or 3 minutes to state some open questions. So the summary is that the main players of the talk are these 2 different ways of modeling quantum correlations. And I told you about Tsirelson's problem, which is a question about whether these 2 ways are the same or not. And so we give a negative answer. We show that these 2 sets are different for some large enough number of settings and outcomes. And the way the proof goes is kind of interesting because it proves a stronger result. The result that it shows is that computing the largest quantum violation, equivalently linear optimization over the set, the tensor palette set, is intractable. So the quantum bound is uncomputable. And the way we did that is by connecting the problem to the theory of interactive proofs that's been developed completely independently in theoretical computer science, but happens to give us a model, this two provers sharing entanglement model, that's directly connected to the problem that we wanted to solve, computation of the quantum bound. I have a couple of minutes for open questions, right?
Yes, you do.
Yeah.
You do.
Okay. So let me
Thank
take
you for a
2-3
great
minutes.
talk.
I have a lot of them. I thought it's a bit too much, but the nice thing is that the talk is recorded, so I'm not going to explain all of them. I'll just put them on the slide and tell you my favorite, and then you can get back to them later or ask me in the questions. So first of all, a set of open questions in complexity theory. My favorite here is okay, you cannot see my cursor probably. Let me try. Okay, maybe you can see this.
We can see it.
My favorite is the second one. So a consequence of our result is that for the study of these multi-prover interactive proofs, any larger number of provers is not more useful, doesn't buy you more power than just two provers. In all cases, you get RE. So the classes of any number of provers bigger than 2, at least 2, are equal. But we don't have a direct proof of this. The only way I know to prove it is to show that MIPS R with two provers equals RE. In particular, when you do this, you don't keep track of the complexity of the provers. So if you're only interested in proving small problems, then I don't know how to reduce the number of provers. So it's a bit, I think it might be a deeper question than it seems on the surface. I like this question. Another one that I should highlight is the fourth question, because this was answered in the archive 3 days ago. So the question was that our result shows that the problem given as input lambda, the Bell functional, n and k is the quantum bound for this lambda, this n and k uncomputable. But then going further, you could ask, what if I fix n and k? Then is the problem given the lambda for these fixed n and k uncomputable? And this was answered, and I can say it later. I'm blanking on the authors. I'm sorry. I know Slostra was involved, but there's a couple of other authors, Fu and Miller. Sorry for that. Fu, Miller, and Slostra showed this. Okay, let me move on to a few questions in operator algebras, because I didn't say so much about operator algebras in the talk. I'm just putting them for the record. The most obvious, interesting open question is a question in group theory, which is a question of whether there exists finitely presented groups that are not hyperlinear. So the notion of a group being hyperlinear is again a notion of some sort of notion of finite approximability. And it's, from a mathematical point of view, it's kind of the natural next step after our result. And finally, there are some interesting questions in terms of verification. In particular, I want to highlight the last question. So all these results about interactive proofs using entanglement, they're very, very sensitive to the prover's actions being perfect. So these provers definitely need fault-tolerant computers. The entanglement needs to be perfect. And there's a very nice result by Yao from a few years ago that shows that if you force the entanglement between the provers to be noisy, then the complexity of the class kind of collapses. It's not exactly clear to where it collapses, but it definitely collapses to some finite time hierarchy. In particular, it gets strictly below RE, and understanding the extent to which this collapse takes place is, I think, an interesting question. So I want to thank again my co-authors, Zhengfeng, Anand, John, and Henry for working together on this project, and also the support of my institution and the Institute of Quantum Information and Matter. Before we close, I want to just flash 2 slides of references, in case you watch this talk later and you want to look up something that I mentioned. So this is some of the papers that were mentioned, and this is, you can't read this, but since it's recorded. Okay, and now I'll stop. Thanks.
Okay, thanks for a great talk, Thomas. So we've got time for a couple of questions from Slack. So just to remind everyone that's listening, if you have a question, please enter it in the relevant Slack channel. Oh, Barbara has a question. So Barbara Tohal is asking, I missed where exactly the unlimited entanglement comes in the RE subset of MIP proof.
Yeah, well, can I move my slides? The short answer is here. Maybe slightly longer answer is here. So the first step towards the proof is just how do you get larger and larger time complexities into MIP stars, so verify larger and larger languages. And the way to do that is that you have to imagine that you're the bounded polynomial time verifier here. but you're delegating to the provers the computation of an exponential time verifier, which itself was delegating to the provers a doubly exponential time computation, which itself was delegating a triply exponential time computation. Okay. And so the provers down there have to prove to you that they're doing all this. They're like simulating this guy who's simulating this guy, etc. And each step of simulation involves proving to you that you're kind of generating questions according to the right distribution, getting the right answers. And these proofs that you're generating the right questions, they involve entanglement tests, like magic square kind of test or some more complicated entanglement tests. And the more, the larger the distribution on questions that you're proving, the more entanglement you need to, first of all, just like do it correctly. So the honest provers also need unbounded amounts of entanglement, and also to prove that you're doing it correctly. I hope that helps.
Okay, thanks. So Laura's also going to read a question from the Slack channel.
Hi, Thomas. Thanks for the talk. So I'm just going to summarize together a few questions. I think you mentioned it already in passing, but perhaps it's nice to clarify again. So how would the power of the class MIP star change if we allowed multiple rounds or quantum messages?
Yeah, I was a bit quick on that. So it's now known that it doesn't change. So it was known before that if you allow quantum messages, whether there's entanglement or not, it doesn't change. So no entanglement, quantum messages or not, it's the same. With entanglement, quantum messages or not, it's the same. Multiple rounds, I think that until our result, exactly the number, and then there's a question about how many provers. So if you allow any number of provers, then it was known that one round is as powerful as many provers. The only thing that was not known is whether one round, two provers is as powerful as, let's say, adding an extra round or adding one or two extra provers. But our result indicates that it's not more powerful. So in the end, MIP star, one round, two provers is as powerful as any kind of extension of it that you might want to consider.
Thanks.
Maybe I can put the question.
So there's maybe just one last final question before we go over to the next talk. So there's another question asking, does the complexity change if you can have if the communication between prover and verifier is also quantum?
No, I think this is okay. I interpreted that as part of the previous question. So
okay,
it doesn't change. It's not obvious. In fact, for the two prover model, the only proof that I know in case there's no entanglement is very indirect. In case there is entanglement, it's due to Wright, Tunger, Vazirani, and they show how you can get rid of the quantum communication a little bit in the way that I described, like all the quantum parts of the verifier get delegated to the prover and tested using a classical verifier. So it's not at all obvious, but it is the case that quantum communication does not help in this model.
Okay, well, thank you, Thomas. Thanks for a great talk, and we'll go on to the next speaker now. I think we're going to take a slight pause in the recording.